Hello. Now we will calculate the electric field due to a dipole. So the first case here will be along axial line of the dipole. So this is the dipole. So we are going to calculate the electric field along this line joining the dipole, along the line joining these charges. So at a point P, we are going to calculate the electric field due to this system. So this point P we are defining with respect to the central point of this dipole. This is the central point. So we are defining the point P with respect to this central point. So this is the point I am taking my axis. So this point P is at a distance x with respect to this O point. And this x is very large compared to the L. And so x is very large compared to L, but this x is not that large so that this dipole, these charged particles will look like they are at the same point. So basically x is large but not too large. Okay. So we are going to calculate the field due to this system. So first what we will do, we don't have right now any formula for electric field due to dipole, but we do have a formula to calculate electric field due to point charges. And this dipole are nothing but 2 point charges. So what I'll do, I'll calculate the electric field because of these 2 point charges independently. Then I'll take the vector summation. So this I'll call as 1 and this I'll call as 2. So first let's calculate the electric field due to this charge. So obviously this is negative charge. So because of the negative charge, electric field will be towards the charged particle. So the electric field due to 1 will be in this direction. I'm calling this E1. And then I'll calculate the electric field because of 2. It will be away from the charge, obviously along the same line joining these 2 charges. I'll call this E2. Now let's write the magnitude of E1 and E2. So the E1 will be equals to 1 upon 4 pi epsilon naught magnitude of charge divided by distance with respect to charge. So you see, this point P is at distance x with respect to center, and this distance is L. So this will be x plus L whole square. That is 1 upon 4 pi epsilon naught q upon r square. That's the formula, and r is the distance of the point with respect to charge, which in this case is x plus L. So this is my equation 1. Now let's calculate E2. E2 will be 1 upon 4 pi epsilon naught q. I'm calculating the magnitude only right now. Q, this distance is again L. So the distance with respect to q of point P will be x minus of L. X minus L whole square, and that is your equation 2. So the electric field at point P will be the vector summation, or you can say the algebraic summation of these two. You see, E1 and E2, they are in the different directions. So EP will be equals to E2 minus E1. Because see, the magnitude wise, this will be a little bit more because this is nearby to the point. E2 minus E1, magnitude wise, this will be the electric field. Now let's take the difference. So if I take the difference, I can take common things outside. So that is 1 upon 4 pi epsilon naught. And q I can take outside. So the remaining thing is 1 upon x minus L whole square minus of 1 upon x plus L whole square. Okay. So this is your electric field at point P. But we do want to calculate this like properly. So what I'll do, I'll take a binomial expansion here. So I'll use the binomial expansion, and before that let's further modify that. So EP will be equals to 1 upon 4 pi epsilon naught q times of x minus L power minus 2 minus of x plus L power minus 2. And now I'll use the binomial expansion, and let's calculate this, take q x common. So 1 upon 4 pi epsilon naught times of q. Out of this equation, if I take x common throughout, I'll be getting x square outside. Okay, and the inside will be 1 minus L upon x power minus 2 and minus of 1 plus L upon x power minus 2. Now let's use the binomial expansion. So from binomial expansion, so binomial expansion is if 1 plus x to the power minus n, that value is equals to 1 minus nx if x tends towards 0. So the value of x is less than, it's tending towards 0. In that case, I can use this relationship. Now, in this case, if you see here, in this case, L upon x, since from that relationship, x is very, very large compared to L, then L upon x will tend towards 0. So this value 1 minus L upon x as well as 1 plus L upon x, it will look like it is 1 plus something 0. So I can use the binomial expansion. If I use the binomial expansion, it will be EP is equals to 1 upon 4 pi epsilon naught q upon x square. This will be 1 minus minus positive. So 1 plus 2L upon x minus 1 minus 2L upon x. That will make EP is equals to 1 upon 4 pi epsilon naught q upon x square 1 plus 2L upon x minus 1 plus 2L upon x. 1 and 1 gets cancelled out. So it will be 1 upon 4 pi epsilon naught q times of, this is 4. It's 4L. 1x square was earlier and 1x we get from here. 4L upon x. Or EP is equals to 1 upon 4 pi epsilon naught 2 times of 2QL upon xq. So you can see this 2QL. 2QL is a dipole moment. 2QL is dipole moment. So this EP will be equals to 1 upon 4 pi epsilon naught 2p, 2 times of p upon xq. So that will become the magnitude of electric field at point P. But you see, electric field we want in terms of vector. So let's come back to this. So direction of this dipole moment is in this direction, because we know the direction of dipole moment is from the negative charge to the positive charge. And when we were calculating this electric field, this E2 minus E1 we have taken, because the E2 is more than E1. So since I'm taking E2 minus E1, meaning E1 I'm taking negative, so this direction I'm taking negative and this direction I'm taking positive. So net electric field is coming in the same direction of EP. This. So net electric field EP, direction of net electric field and the direction of dipole moment, it is same. So if I want the vector formula for this, all I can do, EP will be equals to 1 upon 4 pi epsilon naught 2 times of P upon xq. So this becomes the formula for electric field. This becomes the formula for electric field along the axis of the dipole for larger distances, when the x value of x is more than L, because you see we have applied the binomial expansion here. So this formula we get by using the binomial expansion, and the binomial expansion, to use the binomial expansion, this x has to be more than L. So this is the formula. This formula we have to memorize. This is the formula for electric field along the axial positions. This x we are calculating with respect to the center of dipole. Okay. So this we can memorize, and this is the derivation to calculate that. If somebody asks you derivation, this is the whole derivation. And if somebody asks you the formula, and that formula you have to use in the questions, this is the question. Okay. Thank you.